Hello, students. So what we're going to do today, and next time also we'll do a different result in the next set of videos, is we will prove a result which you surely remember from calculus. It's a very important result which you use all the time whenever you optimize. And here it is, the maximum principal and the minimum principal. Let I equal to the closed interval from a to b be a closed bounded interval, and f from I to r be a continuous function defined on I. Then there is some input c in I, such that for all x in I, well, c is supposed to be like the input that maximizes. So it better be that f of c is bigger than or equal to f of x. C is the input. The is the wrong word to put there. An input which maximizes f over I. And so what this theorem is saying is that there exists such an input. You can maximize continuous functions over closed bounded intervals. Similarly, there's a minimum principle. Let I be a closed bounded interval and f from I to r be a continuous function. Then there's some c in that closed bounded interval, which instead minimizes the function. That is, satisfies the conclusion that f of c is less than or equal to f of x. And let's look at the order of the quantifiers. In each of these, there is some c so that for all x, so it's the same c for every x. This c does not depend on your choice of x. There's a single c which is simultaneously less than or equal to every, for which f of c is less than or equal to every f of x. Collectively, these two are referred to the extreme value theorem, which, just for the sake of convenience, I'll state in terms of soups and infs. Theorem, the extreme value theorem. Let I be a closed bounded interval and f from I to r be a continuous function. Then the supremum of the image of f of I, is in f of I, and the infimum of f of I is in f of I. So let's just go ahead and say a few words about why the maximum and minimum principle, just the maximum principle, follows from the statement of the extreme value theorem, which I'll often summarize as EVT. I'll emphasize the maximum principle. So why should the maximum principle hold? Well, let's do this. So by the EVT, the supremum of f of I is in f of I. So let's remember what that means. What does it mean to be in the image of a function? That means there's some input in I which f sends to this thing. So let's see, by the definition of f of I, there is some c in I such that f of c is equal to this number, the supremum of f of I. That was because of this is an element of f of I. But let's use the definition of the supremum. Since, no, let's not say it this way. So if you like, let's just try to stay motivated. This produces some c in I. Let's read what the maximum principle theorem, maximum principle says. It says that there is some c in I such that for all x in I something happens. So let's go ahead and consider any x in I, we want to show this. So let's try to show that. So what do I know about C? I know that f of C is the supremum of f of I. So f of C is an upper bound on f of I. So f of I is the set of all outputs of the function. Well, f of x certainly is an output. Then f of x is in f of I, so that as f of C equal to the supremum of f of I is an upper bound on f of I, we can make a conclusion. We conclude that f of C is bigger than or equal to f of I. And that's exactly what we need to show if we want to prove the maximum principle. Cool. So if we can prove the EVT, then the minimum principle and maximum principle follow automatically. So my goal is to prove the extreme value theorem. And you'll notice the extreme value theorem has this declaration that I is a closed bounded interval. Let's just explore why that's necessary. Clearly, you need to assume something about the function. If it's not continuous, you're going to have trouble doing much with it. So let's explore this function. Let's see why closed bounded intervals are important. And let's go ahead and start with this. So let's define this function, f from the interval from 0 to infinity, to the interval from 0 to infinity. So shoot, it could just be f from 0 to infinity to r. Let's consider the function given by f. Let's take the function to be f of x equal to 1 over x. In fact, let's define it not all the way from 0 to infinity. Let's define it just from 0 to 1, excluding 0, right? Because you can't divide by 0. I claim that f of 0, 1 is equal to the interval from 1 to infinity. And, right, this is super easy. Let's let y be in the... First, let's let y be in f of 0, 1. So other than the typos, it's easy. Well, then by the definition of f of 0, 1, it follows that there's some input in... Exclude 0, include 1. It follows that there exists some input in the interval 0, 1 with f of x equal to y. So 1 over x is equal to y. And what do I know about this x? We are given that x is in 0, 1. And what does that mean? That means 0 is less than x is less than or equal to 1. Thus, 0 is less than 1 over 1 is less than or equal to 1 over x. So f of x, which is y, is bigger than or equal to 1. That completes the first half of the proof. The other one is also equally easy. Let's let y be in the closed interval from 1 to infinity. What do I want to show? I want to show that y is in that. So maybe I'll do like some scratch walk off to the side. So if that's what I want to show, that means I want to show y is equal to f of x for some x, that's a with x in 0, 1. Well, let's just emphasize this. that means y is equal to 1 over x, and I want to figure out what that x is, but that's easy to solve for x. X is 1 over y. So let's use that. Let's let y be in the interval from 1 to infinity. Let's let x be equal to 1 over y. So I know automatically that y is going to be equal to f of x. I want x to be in the interval from 0 to 1. So let's explore what we know about y and what we can prove about x. So let's see, since y is in 1 to infinity, I know that 1 is less than or equal to y. So 1 over 1, which is equal to 1, is less than or equal to 1 over y, which is exactly what we defined x to be. Nope, that inequality is incorrect. But I also know that y is bigger than 0. In a positive number, you'll get a positive number. So x is in 0, 1. Now, let's look at f of x. So that's 1 over x is 1 over 1 over y. Yeah, that's the same as y. Thus, y is equal to f of x for some x in 0, parentheses 0, 1 bracket. And so y is in f of 0, 1. Neato. So does the extreme value theorem hold for this function? Well, let's think about what the extreme value theorem says. The extreme value theorem says that the sup and inf of f of I should exist. Let's see, f of this interval from 0 to 1, we just showed that it is equal to 1 to infinity. This supremum does not even exist. So the EVT, extreme value theorem, is false over this interval. So let's prove the extreme value theorem. So to prove the extreme value theorem, we need to consider any closed bounded interval I, consider any continuous function defined on that closed bounded interval, show that the supremum of f of I and the infimum of f of I both exist and are in f of I. So let's start even with just this. Those theorems conclude that the supremum and infimum exist. Well, what sort of sets have suprema that exist? Well, these sets, by completeness of the real line, non-empty, bounded sets have sups and infs. So that's what we'll prove first. Lemma 3.3.4, let I equal to AB be a closed bounded interval, and f from I to R be a continuous function, then f of I is bounded above and is bounded below. If we want to show that the sups and infs exist, we need these sets to be bounded. So let's do the proof. Let's prove that theorem. It'll be a proof by contradiction. So setup. Let I equal to AB be a closed bounded interval and f from I to R be a continuous function. We will show that f of I is bounded above. The proof for bounded below is the same, except all the inequalities will be different. Maybe in red I'll indicate I'll do modifications to get bounded below, just so you see that it can be done. So let's suppose for the sake of contradiction that f of I is not bounded above. If you want to prove it's bounded below, then let's suppose it's not bounded below. Consider any natural number n. Is this natural number n an upper bound on f of I? Well, of course not. This set isn't even bounded above. To modify this proof to get a contradiction, well, I'll explore the contradiction for how to modify it to get bounded below in a moment. So what does that mean? I know that n is not an upper bound on f of I. So I know that there exists some element of f of I, and I'm saying y sub n because different choices of natural number will obviously result in different elements of f of I, such that y sub n is bigger than n. I'm going to make that actually legible. Is n, there, an upper bound on f of I. It is not, so we get this conclusion. The modification, if you want to get a contradiction in the case that f of I is not bounded below, you'll see that negative n is not a lower bound. So similarly, you'll cook up some y in f of I such that y sub n is less than negative n. And why am I using n and negative n? Well, that'll be clear in the next sentence. So since I know that y sub n is bigger than n for every natural number n, and the limit as n goes to infinity of n, well, as n goes to infinity, n goes to infinity, so this limit should be infinite, we can conclude that the limit of y sub n must also be infinite. If you want to modify it to make it work for red, well, what do I have? I have y sub n is less than negative n. I have the limit of negative n is minus infinity. So it should be that the limit of y sub n is minus infinity. Nice. So let's think about that y sub n. That y sub n is in, so I have right now this conclusion, y sub n diverges to infinity. I'll get a contradiction out of that fact. So let's see, y sub n is in f of I. So that means there must be some x sub n in I, so that f of x sub n is equal to y sub n. And that's just the definition of what f of I is. Maybe I'll even remind that of you. So saying y sub n is in f of I means, as in is the definition of, saying y sub n is equal to f of something, I don't care what it is, just give it a name, x sub n, with x sub n in I. That's a definition. So, because x, so let's study that x sub n now. That x sub n is in I, which is the closed interval from a to b. So that means x sub n must be between a and b. It must be that a is less than or equal to x sub n is less than or equal to b. Since this is true for every natural number n, I see that b is an upper bound for the sequence x sub n. A is a lower bound. So this sequence is bounded. I can apply the Bolzano-Weierstrass theorem. The Bolzano-Weierstrass theorem says that every sequence which is bounded above and bounded below, so every sequence that's just bounded, has a convergent subsequence. So this sequence has a convergent subsequence. Let's just give it a name. Let's let x sub n sub k be that convergent subsequence of x sub n. Since that subsequence is a convergent subsequence, it has a limit. Let's let x be the limit of x sub n sub k. I'm really close to getting this contradiction. So right now, what do I have? I have for every k and n, x sub n sub k. Well, I know that this is true for every n, right? I know for every n, x sub n is between a and b. N sub k is certainly a natural number, so x sub n sub k is also in I, the interval from a to b. So I know that a is less than or equal to x sub n sub k is less than or equal to b. And I know that's true for every natural number k. I can pass to the limit because I know the limit exists, right? The middle term actually has a limit. So I'll be able to conclude that a is less than or equal to x is less than or equal to b. Oh, neat. That means this limiting value, x, is in the closed bounded interval I, f is continuous on all of I, so f must be continuous at this input x. Parentheses, because f is continuous on I by assumption. So it has to be continuous at each input in particular. Oh, so let's see what we have. I now have a sequence x sub n sub k. So let's go off to the side. I have the sequence x sub n sub k is a sequence of elements of I, but I won't even say I, I'll say the domain of I, which converges to x. I know that f is continuous at this point x. Oh, but I proved something in exactly the previous lecture about continuity in terms of sequences. That means that f of x sub n sub k should converge to f of x. So let's maybe even remind ourselves what what we proved in theorem 3.2.2. I'll paraphrase because I don't want to look it up verbatim right now. So theorem 3.2.2 says, and you can look it up on your own. You have your own records of my notes. Says that f from, I don't remember what I called this, at x to r is continuous at some point p in x if and only if for every sequence x sub n of elements of x which converge to p, f of x sub n converges to f of p. And I'm in exactly that sequence now. This function f is continuous at this input x. X sub n sub k is a sequence of elements of the domain of f, the thing called x here, but it's called I in the theorem, which converges to this input x. So it must be that, maybe I'll say it in words, f of x sub n sub k converges to f of x. Neat. So in particular, that means the limit as k goes to infinity of f of x sub n sub k exists. But remember, f of x sub n is y sub n. Right? That's how we chose our x sub n's. So that must mean that the limit as k goes to infinity of y sub n sub k exists. But we just showed that the limit as n goes to infinity of y sub n is infinity. Oops, I said I would only do the modifications in red. So what do we know? We know that y sub n diverges to infinity. So since y sub n sub k is a subsequence of y sub n, it also diverges to infinity. I claim this is a contradiction. Why is it a contradiction? Well, here I see that the y sub n sub k converges, but here I see it diverges to infinity. There's my contradiction. Oh, and let's do the modifications. So if you are doing the red case, you would instead have a negative infinity here and a negative infinity here. So we've gotten a contradiction, so that the thing that we assumed was true must be false. So it must be, in fact, that f of I is bounded above. And if you went through the modifications in red, you instead got that it is bounded below. Great. I'll stop here and resume in just a moment with the proof of the extreme value theorem. This lemma will be important. It'll be used in the proof of the EVT. Great. Talk to you in a moment.